Right, Dropbox, DIFC, workbook, physics, atoms, lesson 2. Okay. You two missed the last lesson, didn't you? Did you watch the video yet? Oh. No? Did you watch the video yet? Oh, okay. Okay. You know you should. Alright, radioactive decay equations. Because we start a new chapter, you know? Got that? Yeah. Got that? Okay. So, Matt, you got that? Yeah. Okay. Right. Do you study this element in chemistry or not? Does it not come up? No. Now, the people here you were here for the last lesson, weren't you? Or you were, yeah. You two, have you heard of this element before? Cba and yeah. You've heard of uranium before? Yeah. What do you know about it? Like where do you think you've heard it before? Oh, any ideas? Like I just mean, would you have heard it TV, movie, class? Where do you think you've heard it? Yeah, like what's it used for? Or what's it used for? Or what can it do? What's so special about it? What's so special about it? Any ideas, Kim? Have you heard of this before? Yeah. So last week we were talking about radioactive material. So uranium is radioactive, so it releases radiation. And we said there are 3 types of radiation that's released. Alpha, beta, and gamma. Okay, so there's 3 types. Uranium releases radiation. We learned that radioactive isotope like uranium-239 will decay. Oh, oh dear. Now I'm sick. Alright. We learned that an isotope like uranium-239 will decay, and the energy released is in the form of alpha, beta, or gamma radiation. But how can we detect this radiation? Because, you know, we were saying last time that radiation is harmful to your health. It's not something you want. So we would like to detect it, but there's a problem. These are properties of radiation. Firstly, it's colorless. So radiation doesn't have a color. So that means you can't see it. Okay, well, maybe there's other things about it. It's odorless. What does that mean? You can't smell it. Alright, well that's a problem. It's tasteless. Don't even think about doing this. You can't taste it. Alright? And it's chemically inert. What does that mean? It won't react. It won't cause a chemical reaction. But it's very important that we can detect radiation because it's so dangerous. But we have these 4 properties that make it difficult. So all I need you to write down is these 4 features of radiation. That it's colorless, odorless, tasteless, and chemically inert. Whoops, the heck. Oh, don't do that, don't do that. I'll need to play a little sound in a second here. Okay, you got that? Yep, not yet, okay. Oh, Wi-Fi is terrible. Right, you got that, Andek? Okay. Alright. So, before we talk about detecting it, we have to say exactly what we're trying to detect. So we have this thing called the activity. And it's the rate at which unstable nuclei decay, disintegrates. So, just before you write that down, let me just explain exactly what I'm saying here. Let's say you have something like uranium-238, or what was it, 239? Which was it, 38, 39? I think it was 239, yeah. So here's your uranium. And it releases alpha, beta, gamma. And as this is released, the amount of uranium you have is reducing. So it reduces over time. Okay, so, you know, if you start off with 1 kilogram, you won't have 1 kilogram of uranium forever. It's like it's, you know the word crumbling? Like breaking apart as the radiation is released. So it's disintegrating. That's the word we say in physics. Crumbling, breaking. Okay. So the way we measure the activity is how many pieces of uranium we lose per second. How many isotopes of uranium are destroyed in a second. That's called the activity. So you can just write it's the rate at which the nuclei decay. Okay, you got that? Yeah? Okay. So the way we measure it is called the becquerel. I'm not exactly sure how to pronounce it because it's a French name, so I can just say BQ. I think becquerel is perhaps right. It's the SI unit, and it's defined quite simply as 1 becquerel is defined as the disintegration of 1 nucleus per second. So it's one destruction per second. Got that? Yeah. In other words, when 1 nucleus is destroyed per second, we say the activity is 1 BQ. Now, I just want to be clear. Really, if we want to be careful with the signs, we say minus 1 BQ because we're losing 1 atom per second, 1 nucleus per second. Okay, but the context when we talk about radiation is that we're always losing nuclei. So very often we don't bother writing the minus 1. Okay, it's a bit like everybody knows you're losing it, so what's the point in writing minus 1? So sometimes you might see me write just 1, but it's really minus 1. Okay. And we can know it's minus because we talk about the disintegration. So, you know the way when we talk about acceleration, you have deceleration. The D means the minus. So, A represents the activity. For example, 5 kilo becquerels means 5,000 nuclei destroyed per second. N represents the number of atoms. For example, 10 to the power of 6 atoms. And sometimes I'm a little careless, or a lot of people are careless with the A. Really, A is a negative. But just like with acceleration, we can drop the minus if we use the right words. So for example, if I said the activity rate for the destruction is 5, because I said the word destruction, we understand that's really a -5, that we're losing 5,000 per second. Calculating n is not too difficult. You learned how to do this in materials, you know, PV equals nRT. So we've done this already, and you've done it in chemistry. For example, 12 grams of carbon will have 1 Avogadro's number, isn't it? Is that right? 12 grams of carbon is 1 Avogadro number of atoms. Have I got that right? How many atoms in 12 grams of carbon? Is 12 grams of carbon 1 mole of carbon? Isn't it? You're the chemistry students, you should... You are chemistry students, aren't you? Yeah, it is. Yeah. Don't let Lorraine hear that you didn't know that, okay? Isn't carbon 12 is like used as the definition of what 1 mole is, I think. Yeah, okay. Anyways, we'll continue. Anything you need to write here? I don't think so. It's okay. Right, this is how we can detect radiation, and I'm going to try and play a sound of it because maybe you've heard this sound before. So, have you heard these sounds before? Maybe even in movies or video games? Are you sure? Because they said there's one here from like Fallout 5. This is a sound you haven't heard before? Okay. It's, here, maybe I should show this one. This is a little digital one. Can you see this? So this person here is entering the evacuation zone from Fukushima nuclear power plant. You know what? See how loud it gets. So when you hear that little... Okay, let's try that. By the way, you shouldn't really... Okay. Yeah, they drove too close. You shouldn't really drive into nuclear disasters like these people are. But that sound you hear, that's hearing... it's like you can hear the radiation. Every time the radiation hits the detector, it makes a click sound.
This radiation, it comes into a car.
Yeah, because they're you know what happened in Fukushima in Japan? They had the nuclear disaster. So the area is radioactive. Okay, so this, well, the one in the car is a small little digital one. Okay, this is how I always picture them from school. They're much smaller now. This is called a Geiger counter, sometimes just called a Geiger counter for short, or GM counter. And this lets you detect radiation. And you see on the screen it has counts per second. That's remember we said the activity is the becquerel, which is like 1 destruction per second. So each click you hear is a destruction per second. I will show you now how these work, I think, in the next slide. But you should at least write the name down, Geiger counter. Okay. Now, how does the counter work? It's pretty simple. It's not a complicated device. So what you have here is you have the anode, which is positively charged, and then you have the cathode here, which is negatively charged, and then you have this large voltage, 500 volts. Now you know what happens here. It creates an electric field. And do you remember the formula for the electric field we said is V over D. Okay, so the V is pretty big and the D is pretty small. So the E will be pretty big. Okay, and you also know F equals QE. So if you have some charge in the electric field, you get a force. So can you see here the atom, there's atoms in here. What's inside of it? They fill it with a gas like helium, maybe? I think I have it on the next slide. No, not helium. Something else. Can't remember right now, but I have it on the next slide. Anyways, there's a gas that's filled in here. And when the radiation comes in, we said it ionizes the atom. So you know from chemistry what happens when you ionize an atom. You release the electron. Yeah. So can you see here the electron is released and you're left with an ion. What charge will this ion have? Positive, because it lost an electron, right? And then the electron has a charge of a negative. So what happens is the electron hits the anode and the ion hits the cathode. And this detects the change in the current. So the current, you know, there's a little sort of blip in the current. If you could picture it like you had an ammeter, you have the time, you have the current. So the current should be constant, but then when the electron hits it, you get a little bloop like that. So all that happens is they just change that into sound. So then you can hear it. So you see it's very, very simple. This is a mica window, not a glass window. Mica is a very, it's different to glass. It's like, I can't even explain what it's like. Anyways, it's not quite like glass. It's transparent like glass though. It lets the radiation in. This only works if the gas is kept inside. So if this window breaks, it doesn't work anymore because you need to have a gas in here, like I think like helium. So it's a very simple machine. Really, it's kind of like an ammeter. It just detects the change in the current. So it's really good at picking up beta radiation. I think is the best one it can pick up beta and gamma. But we remember last time we said with the alpha radiation, you're actually able to block alpha radiation with your hand. So I'm not even sure that much, I don't even think any alpha radiation can get through the mica window. I think it's really only just beta and gamma. But that's okay, because usually where there's alpha radiation, there's also beta radiation as well. So you can pick up the beta radiation. And I would need you to draw this, but let me just check if I have it on the next screen. No, I don't. Let me look it up. While you're drawing that, I'll tell you what gas is inside of it. No, I was right. You can use helium, argon, or neon as the gas inside of it. So we'll just say helium. It's easier. Now, you might be wondering how long these Geiger counters last, because when the radiation comes in and ionizes the atom, then it means you have one less atom that you can ionize in the future. So if you're wondering, there's about 10 to the 9 helium atoms in here. Once all those atoms are ionized, the Geiger counter doesn't work anymore. You'll have to fill it back up with helium, fresh supply of helium. I guess that shouldn't be difficult to do. You got that? Yeah. In the 1950s, you know, of course, that a lot of countries were looking to build their nuclear weapons in the 50s. So it meant radioactive material was very expensive and very valuable. A lot of people bought Geiger counters so that they could search for radioactive material to sell to the government. So it's okay. So you probably don't have one at home, but you know, they are quite popular in some countries where, a bit like gold, people go searching for radioactive material. But I don't think there's any places in Ireland that you can search for it. I think, as far as I know, a good place that has a lot of radioactive materials in the earth is Australia, I think. I think Australia has uranium mines, I don't think there's any in Western Europe. There's certainly not any in Ireland. Okay, so we have our first equation. Activity is proportional to the number of atoms, and the activity and the number of atoms is always decreasing, therefore A is always negative. Mathematically, we have basically this formula. A is equal to minus lambda n. So what happens is, you have a material like uranium, and you have some radiation coming off. So for example, if the activity is minus 2 BQ, that means per second you lose 2 atoms of uranium. Okay? But what happens is, as you get less uranium, so maybe you have half of it now, the activity, you also get half the activity. So you get half the radiation. In other words, it's proportional. As the radioactive material decreases, you get less activity, and just everything is proportional. So the formula is quite simple. The activity is a constant times the n. If you have a big N, you have a big activity. Small n, small activity. It's all quite simple. The lambda is called the decay constant. So a big lambda means a lot of decay and radiation. And the minus is to show that the n is decreasing. So this is our first formula for today. Yeah. By the way, the Geiger counters, they don't work so well if the radiation is really, really high. Because what happens is, in the picture, if you have so many little pulses so quickly, then the machine can't see a little spike. You know, it's like if I hit this, you can hear it. But if I hit it so fast, then at some point you won't be able to tell that I'm hitting it, you know. So if your Geiger counter is getting louder and louder and louder and then suddenly stops, that doesn't mean that you're safe. It just means that it can't pick up the radiation anymore. Okay, so if you're ever in that situation, just remember that, all right? You shouldn't think, oh no, it's okay, it stopped now, I'm fine. It's not true. Okay, so what are the units for lambda? Alright, well let's have a look here at the units here. We have our formula A equals minus lambda n. The n here is just the number of atoms. And remember we said the activity, so it's not really a unit. The activity is, oh no, okay, we can say atoms. The activity is becquerels, which means number of atoms destroyed per second. So you can cancel that with that, and you get lambda, its unit is per seconds. Does anyone remember what per second is? There's another name for per second. Think back to mechanics. No? Are you sure you don't? I think you do. Do you remember this unit? Hertz? So the lambda unit is per second, or also called the hertz. Okay, so I think you should make note of that. Got that? Yep. Right. In a radioactive sample of 1 mole of atoms is destroyed per second, what is the activity? Okay. What is the activity? Right, so in this question here, I said you have your uranium, and I said that you lose 1 mole per second. So that means the activity is minus 1 mole per second. Although we don't use moles, we use number of atoms. So how many atoms is 1 mole? It's 1 Avogadro number, yeah? So the answer is minus 6.02 times 10 to the 23 atoms per second. And atoms per second, we call that a BQ. So the answer is roughly minus 6 times 10 to the 23 becquerels. That's the activity if you lose 1 mole per second. Is that okay? As a simple example. Is okay, Matt? Yeah. So, alright. Let me give you this one to try. You have 10 to the 10 atoms. 1,000 atoms are destroyed per second. What is the lambda? Okay, so using your formula, tell me what the lambda is. Try and work this out. Okay. Oh, calculator time, okay. Got that? Yeah, yeah. So, if I use the formula, A equals minus lambda n, What's the A here? 1,000 atoms are destroyed per second. So that's 10 to the 3.
Is it minus 1?
Very good. I was just about to say that and then I forgot to say it. You're right, minus. And the N is 10 to the 10. Alright, so the lambda looks like it's 10 to the minus 7 per second. Okay, that's fine. Right. Define activity by expressing it as a derivative. Now, remember, for example, force is the rate of change of momentum, so that's dp dt. And you've done differential equations with Joan. Yeah? So, what do you think activity might be as a differential equation? What could you say A is? D something, D something. Now take a minute, look at the definition of activity, or think about what activity is, the units. What might we say it is as a derivative?
d over dt.
You're half right, you got the dt right, but it's not going to be dA. It's going to be something else. What is it, Matt? Good, okay, so it's dN dt. Right, so you'll need to write this down. A equals dN dt, and also A equals minus lambda n. So, if I sub that into that, I can get dN dt equals minus lambda n. Yeah? Yeah? Okay. Now, this should remind you of something from maths class. Does it remind you of anything you've done in maths lately? Yeah, what are they? Ah, yeah, what are they called? Yeah. What's the lesson called?
Seems familiar, but I forgot the name.
Matt knows what to do, but he doesn't know the name of the lesson, I think. You don't know the name of the lesson? Differential equations? Ordinary differential equations? Yeah. So what do you do, Matt? You have to move something. What should we move first?
Move dt to the right.
Move dt to the right,
And to the bottom.
and then n to the bottom. Like this. You've done this in maths class, right? Yeah? Yeah? Okay. Alright. Alright, Matt, you're on a roll. What do we do next? Good? Okay. Can I scroll down a little bit? Right, what do I do next? Do you know, Siva? Do you know what the integration of 1 over n is? Very good, you do know. Alan. Okay, and Kim, would you know what this becomes? Integration of lambda? Lambda is a constant. Very good. And we have our plus c here. Okay, continuing. How can I cancel the log? E. So I'll put an E here and an E here, and I'll get n equals E minus lambda t plus c. Okay. Got that so far? I can scroll down? Yeah? Now, we'll say when t is 0, we'll say n equals n0. So n0 represents the n at the start. So that means n0 should equal E0 plus c. So that's equal to EC. So c would equal log n0. Okay? Are we okay with that so far? Oh, I can't see. Is that okay?
Yeah.
If I go back to this line now, I have n equals e minus lambda t plus log n0. That's equal to e log n0 e minus lambda t. Now what's e and log? What happens? E and log, what happens? Here. Yeah, they cancel. So you're left with n equals n0 e minus lambda t. That's the formula for n. We've proved it. So if you have time here, n here, and something like uranium-239, and it's released in radiation, the number of atoms of uranium that you have decreases exponentially. So you have this shape you've seen in maths class before. Yeah. So it's not. I like doing this proof because it's similar to something you do in maths class at the same time. So, are you still doing these in maths class, or have you moved on to something else? Have you gone on to vectors? What are you on now? Are you still doing integration? Graphs? Oh, are you doing domains and mappings, or sine inverse, cos inverse?
Yes, sine inverse. Cos inverse, I think.
Yeah. Yeah, you should know what you're doing. It'd be good. Okay, continue. To find the value of n, or a, we can use the equation, which I've done. So we have this result. Now what's really nice is, okay, I did this one for you, but with not too much difficulty, you can also show this one here. In fact, actually I can do it right here. So what I do, take this line here, I'll multiply both sides by minus lambda. So I get minus lambda n equals minus lambda n0 e minus lambda t. Well, what did I say minus lambda n is? A. And minus lambda n0 will be the activity at the beginning. So very easily you can prove the other formula here. The activity is also exponentially decreasing. Okay? Yeah. It's okay? Yeah. Right. Okay. So we just have the one example to do, but it's a big example, but it covers all the formulas. A sample of iodine 134 has a mass of 268 grams. The molar mass is 134 grams. The initial decay activity, so that's the A0, is 1.32 times 10 to the 20 BQ. Right, so let's do this one together. Initially, how many moles of iodine are there? So how many moles of iodine do I have? Who can see that?
So it's multiplied by Avogadro's constant.
No, I'm looking for the moles, not the atoms. 2. Because I have 268 grams of iodine, the molar mass is 134, so it's just 268 over 134, so that's 2 moles of iodine. Is that okay? B. Now, how many atoms of iodine do I have? So that's what you said, Andek. I'll have to take the 2 and multiply it by Avogadro's number. So the answer is I have 12.04 times 10 to the 23 atoms of iodine. Okay? Right, so before I continue, I'll let you write this down, A and B. You can just write it down again. And then tell me what C is. Okay, so A, B, C, please. I've already shown you what to do for A and B, so just A, B, and C. Okay, do you have this lambda? Yeah? You have the lambda? So we should use the formula A equals minus lambda n. So that means lambda is A over n. Now what's the A? It's 1.32 times 10 to the 20. And what's the n? It's 12.04 times 10 to the 23. Yeah? Is that what you did? What answer is that, please?
1.1
per second. Okay. Is that okay, Siva? Is that what you did? What went wrong for you? Okay, okay. Is it okay now? How many atoms of iodine are remaining in the sample after 1 hour? So which formula do you use here? I want you, yeah?
Never mind anything about it.
No,
It's
for
1 hour, right?
1 hour, yeah?
And the last question is for seconds.
Yeah, so it means we'll have to convert the hours into,
So multiply 2,600.
yeah. So I want you to use this formula now to tell me how many atoms you have after 1 hour. So D, please. Yeah? Did you get an answer? You got the same? Very good. Okay, what's that? 8.1 times 10 to the 23? Okay. Right. E. What's the activity? Well, that's easy peasy. You just use this formula. You know lambda and you know the n, so you can get the activity. So, what's the activity after 1 hour?
$8.91 times 10 to the
8.91 times 10 to the 19 BQ. Okay. How long until you have only 100 grams of iodine? Right, now we need to work out how much that is. So what did we say? 284 grams is what we had at the start, and that's equal to 2 moles. Isn't that what we said? And that's equal to 12.04 times 10 to the 23 atoms. Okay, and I need to know 100 grams. So what do I need to do? I need to multiply this by 100 over 284. Yeah, okay. So can somebody just multiply this by 100 over 284, just this one here? What do we get, please? Just 12.04 times 100 over 284. Hmm? I shall tell you once I get the answer. What is it? 4.24 times 10 to the 20. So, Matt, we have 284 grams. If I multiply 284 by 100 over 284, what will I get? I'll get 100. True? So if 284 grams represents this many atoms, likewise, if I multiply by 100 over 284, then I'll know how many atoms I will need for 100 grams. It's a trick, it's a maths trick. I have 284 grams. I don't want 284 grams, I want 100 grams. So I'll multiply this by 100 over 284 and I'll know how many atoms I need for 100 grams. That's what I'm doing. Is it okay? Alright guys, so using the formula from earlier, 4.24 times 10 to the 23 equals 12.04 times 10 to the 23 E minus lambda, what's lambda? What was lambda? 1.1 times minus 4 T. I want you all to solve this for T, find T. You did this in maths class in semester 1 when you did exponential equations. So what should we do first here? I think what I would do first is just get rid of those guys. Cancel them. And then I would divide by the 12. Okay, see if you can get the T. Remember, T is in seconds, so you might need to change it to hours because it should be big, I think. So try this for a minute. Okay, how are we doing?
2 hours.
Yeah, give it to me as hours. What did you get, Matt?
2 minus 6, 4.
So about 2 hours and 40 minutes, about, roughly. Maybe more like 39 minutes. Yeah? Were you able to get that, Seba? What's that? Okay. Do you know what to do? Yeah. So we divide by 12, then we take the log, and then we divide by minus 1.1 times 10 to the minus 4. Okay. The last part is how long until there's only 1/4 the activity? Okay. So what did we say the activity at the beginning was? What was the activity at the beginning? I gave it in the question, didn't I? There it is, 1.32 times 10 to the 20. Okay. Seba, can you just type in 1.32 divided by 4? One sec, sorry, what did you say? Okay, so that's the activity, and then that's the activity later. Right, once again, guys, I want you to use this formula to tell me what the t will be, please. So you know the a, 0, the a, and you know the lambda, so try and solve for t here. Yeah? What'd you get? 8 hours?
3.5.
3.5 hours, okay. $3.5? What did you say? 3.5? Are you sure? So you have you have 0.33 times 10 to the 20 equals 1.32 times 10 to the 20. E minus 1.1 times, what was the lambda? 10 to the minus 4 t. So I divide this and I get 0.25, of course, yeah. And I log it, get rid of that. So the t will be log 0.25 over minus 0.00011. Is it? No. 1, 2, 3, 4. Yes. And what does that come out as? That is what you said, is it? Which was what? Sorry. 3.5, 3.5 hours. 3 hours and 30 minutes. Oh yeah, no, sorry. Yeah, you're right, Matt. Sorry, I was thinking of something else. Okay, you got that written down? Yeah. So what we'll do next, we'll do a tutorial on the last homework, and then if there's a little bit of time, I'll let you try the questions for this homework. Can I close this? Yeah. Right.